So hey guys, how's it going? Today we're going to be talking about how throughout the past year, the API team at Twilio has been working to essentially program itself into obsolence. Quick note, if anybody wants to take pictures of slides, don't bother. There'll be a slide at the end that has a link to where the slides will all actually be on speaker deck. So really convenient. Just take a picture of that. So my name is Carlos. I'm on the API team. And to give you an overview of what the API team does, this was our responsibility in last year. We were looking at Signal. So we manage and develop the public API proxy layer. The Twilio API is a federated API, which means that all of the REST API requests come through the API team's infrastructure and then goes and talks to backend services like calls and messages and such to actually do things. And we also manage the public REST API and the helper libraries. The helper libraries for the REST API, which so these are like the Ruby, PHP, Node, etc. libraries that you guys use to interact with the Twilio API without having to actually deal with HTTP. And so if we looked at how a product essentially comes from inside a project into an actual product you guys can use, this is kind of like what the pipeline looks like from the API team's perspective. We get a request from a product team that says, hey, we're ready to go. We have, for example, wireless, or we want to expose this to customers. And so what do we need to do, API team? And they're like, all right, well, what's your API look like? And then we develop server-side resources, which basically turn exterior requests from customers into requests that the downstream service likes. And we take those responses and we spit them back out to customers in a way that they like. Then we also need to make some integration and cluster tests. Our cluster test and integration test suites are very strong because they're kind of like the last line of defense against errors in the API. So they'll catch anything like a downstream service that's misbehaving because of a change in another API, for example. So that takes a little while to actually develop those tests and make sure that they're strong and consistent. And then we'll go and develop the actual libraries. We'll add features to existing ones, or we'll make new resources in our libraries for new products, and we deploy all that. And so last year when we were looking at the way we develop products, all these boxes take a lot of time. So there's a lot of big blue boxes, and there's a lot of manual work that goes into developing these resources for the API. So we wanted to see if we can actually make this more efficient, because this is becoming a big blocker for making new products. And we decided to first look at that library square, because this is something that other companies are already approaching. And so we have these 6 helper libraries in these 6 languages. And some of them were developed by dev angels over the years. Some of them were developed by salespeople. They weren't all developed at once through one cohesive structure. So as a side effect, they all have different paradigms and such. And some of them have different paradigms within themselves and how you do things. So they're not an easy target for generation, but we wanted to see if we could essentially get from one source of truth and then generate all these libraries. So before we went and actually built something for this, we of course looked at existing solutions, see if there's something we could just plug in and use. So these are 2 examples of things we looked at, Swagger and gRPC. These are commonly used throughout the internet now. You'll be able to find a lot of information about them. And they're used to generate helper libraries for different APIs. And when we looked at Swagger, the specification was a little too closely tied to HTTP for us. Because it had to basically cover any possible API, it was very verbose in how it handled where things were and how you would define things. It was very low level because of that, and the actual resulting libraries, because they had to kind of work for any sort of shape of API, they weren't super easy to use, and our libraries need to be very, very easy for customers to use. That's kind of our bread and butter at Twilio. Then gRPC was also very low level. This makes sense because gRPC is a little more powerful in how it's able to do things. It's able to handle really advanced HTTP, things like multiplexing and such, and it deals more with the transactions than the actual resources. So it was basically a little bit of overkill for us, and we didn't really need that. And it was also, the resulting libraries were also a little bit too unassuming. So satisfied that we didn't have not built here syndrome, we decided we need to build something to actually get something we want. So first we have to define what our requirements are, right? So what do we need? Well, we need a declarative way to define our API. We don't want something that can be kind of programmed and jerry-rigged, because that makes refactoring later kind of difficult. If some people are able to basically put a bunch of loops in their definitions, then it's a little difficult to work with later, and it's very easy to make bad practices. We need to generate the helper libraries automatically from these definitions. And the definitions need to be as small as possible and as easy to read as possible. The end goal is going to be for product managers to actually make the definitions themselves. So instead of getting a spec and a Google document or something, we would actually get a declarative definition that programmatically defines what this new resource or product looks like. We also need a strong integration test suite, just like our server-side resources. We want our client-side resources, libraries, to have very strong integration tests so that we know when we're shipping something that it is strongly verified and we don't have to worry about it breaking. And the definitions need to be powerful enough to express any new product we come up with, but restrictive enough that they stop people from making any bad practices or stop us from not noticing bad practices before it actually reaches the customers. And so the solution we came up with is a project called Yoyodyne. And Yoyodyne is a code generator that uses definitions expressed in JSON that is designed to derive a lot of information from very little amount of actual information given. So the definitions don't contain a ton of information about how to actually do things. It explains the bare minimum, and we derive a lot from that. And then every feature change in any helper the helper libraries should require one set of changes to these API definitions. We should not have to make a change per language, because then we're kind of defeating the point. So this is kind of how the architecture of Yoyodyne works. We have these set of definition files, and I'll show you kind of what that means in a little bit. And then we throw them into these controllers, and each language has their own controller, which they use different shared views that are actually able to generate the actual text of code. And then it spits that out into artifacts. And so this is kind of like, you can see this model view controller, right? So the definition of the model, the controller's here, and then you have the views that it uses to actually generate code. And if we look at the definitions, this is like what they kind of look like if you look at the folder structure. So we have these base definitions, genes, transactions, types. So we're going to go quickly and see what these are. So if we look at, for example, the base definition for calls, it looks kind of big and menacing, but it's actually really simple when you get down to it. It's just like calls that has a lot of fields. So what these base definitions are designed to do is define what the resource is, what it looks like, what actions can be done to it, and what the relationships are. We're not dealing with anything specific to HTTP. We're not dealing with anything specific to like how you like curl something on the API. We're just dealing with the object model of the API as REST resources. So if we look here at the top, what it is, we can see like different names that we might use for referring to calls. We can look at its location on the Twilio API and the location for its list and instance resource if it has them. We look at, we define what it looks like, so we can see like if it has different enums, so what values can actually reside in there, what properties does it have, what types are those properties, what specific types are the properties. For example, like date times, is it RFC 282 or is it ISO 8601? What can we actually do to this resource? Can we create it? Can we delete it? Can we update it? How do we do that? Here, for example, we specify like a method post because this is an HTTP resource. So we say like, what kind of method is this? What properties are required for each of them? Which ones are optional? What can we pass in? How do we build this path? Where do we put the SID? What type of SID is it? The relationships between them. So we actually know that, for example, calls have recordings, they have notifications, and they have feedback. So it's like how do those define what properties does calls have that we need in order to get a recording? So for example, the call SID and the account SID. What components does it have? These are basically, components are just relationships, objects that you don't need the actual call SID for. It's just like something that's on all calls. And then we have the types, and this is the only resource that's developed per language, but there's only one per language. It basically shows which semantic types map to which language types in the when you're actually generating the libraries. So for example, this is Java, and you can see like, string will be a string object, and map of string and string is like a URI map. And then, so we also need these transactions, because when we want to auto-generate the integration tests, we can't use the base definitions for that, because then we're not really testing anything. We're just testing that the base definitions we wrote actually generate code that work out the base definitions. But we want to verify that the code we wrote is actually working for the API that we're developing for. So the transactions are the actual recorded interactions with the API. So it'll be like, like VCRs of what we actually get when we hit this API, and what we request and what we respond with. And this satisfies this kind of error gap we want to work with, where we don't want the integration tests to actually use any of the base definitions to actually generate their automatic tests. And then lastly, because we were kind of, our initial target is to try to generate the existing helper libraries that we have right now, we have these compatibility definitions. And these basically say like, there's some weirdness in our current libraries where, for example, in Ruby, the available phone numbers, locals, actually just all wrapped up into one available phone number class. And so we had to tell Yoyodyne that. That, however, that last one was a problem because we discovered through development that we were making a change for each language, which is not what we wanted to do. We wanted to prevent that. So the compatibility definitions were kind of like making everything really complicated, but we didn't really want to have to deal with this in the future. So we decided we had to regroup and rethink our approach. And up until now, we were kind of trying to avoid making any breaking changes to our existing libraries. We don't want customers to have to basically make changes to their existing code to upgrade to the new hotness. And we also don't want to make it, so we don't want it to basically break customer code if they want to upgrade. But at this point, it's becoming more work to actually develop the generators for these libraries than it is to just manually develop them. So we decided, look, breaking changes need to be made. And if we're going to be making some breaking changes, we might as well make a bunch of breaking changes and make them just way better. So we identified a couple of things that the people have brought up over the years and things that we've noticed that have been troubled for customers. And we kind of identified these pain points and we said, okay, if we were designing libraries today, what would they look like? And we did that. But more importantly, the internal structure was more conducive to auto-generation. And so this is kind of like an example of the, before PHP, and now it's kind of much more language idiomatic. So now that we have this library generation from these definitions, we see that we've kind of changed the square into a much smaller square of creating Yoyodyne definitions, and then we get automatic library support, which is great. We still have all these other squares though. So what can we do about that? Well, so in order to tackle the server-side square, we need to see what that actually involves. So our server-side resources are all defined in declarative proxied resources. And what this means is like these are basically Python code that determines what fields this resource has and how you actually interact with the backend. If you want to know more about this, Sam Kimbrell is giving a talk, I believe, at the exact same time and place tomorrow. That's going to be in-depth about how we actually do this federated API layer called Starship. So we need to basically automate this part. And at this point, we're kind of determined that we're kind of being the gatekeeper when we have these DPRs we have to make. So we want to get out of the way of product teams and let them essentially provide us those definitions and then automatically have that not only the client-side libraries, but the server-side resources. And the solution is CPR, configured proxy resources. And so from the Yoyodyne definitions, we know what a resource is supposed to look like. We know what we can do to a resource, and we know how to do that. So really all we need is a way to determine how to interact with the backends. And so for this, we have CPR definitions, which are an additive to the base definitions, just like types and just like compatibility and such. And these determine how we actually, what downstream resources we talk to. So for example, the wireless API, we might talk to a wireless service. And we say like, well, these are transforms you need in order to make the wireless API work nicely with the external customer. And so with that, we're able to eliminate that server-side resource and make that box one kind of nice small box. So whenever we make we got the base definitions from the product team, we're actually able to automatically generate the CPRs for the server-side resources and libraries without any real work from us. It's just running one command essentially. And then we still have to make these integration cluster tests and deploy, which is something we still want to tackle, right? Because that's still kind of manual work. We want more red boxes, less blue boxes, less work for us. So in order to generate these cluster tests, the trick is we need to know how to generate resources that the resources depend on. So for example, if I want to make a call, I need a phone number. But the call resource doesn't belong to phone numbers. It like has a hidden dependency sort of where that to field needs to be a Twilio phone number. Or sorry, the from field needs to be a Twilio phone number. So we came up with this idea of genes. It's essentially to define relationships between fields in the Twilio API. So you can see, for example, in the calls resource, there is a gene defined there. It's a voice origination number. And if we go back here, that'll map to either an incoming phone number or an outgoing caller ID. And then from that, we're able to generate a couple things. So for example, we were able to generate an automatic availability test for run scope. So we're able to, anytime we have a new resource, that will automatically have not only internal tests on the library, but also availability tests that actually make sure that the library's, the API is working at all times. We can make little dependency graphs here to see what our API looks like. And we can make the cluster tests. So the cluster test uses the dependency graph to actually say like, well, I need a test that I can make a call. Well, let me go make a phone number first. That works, cool. Now I can make a call. So we're doing a full end-to-end test automatically as we run these cluster tests. And so now from the API team's perspective, this is what the product pipeline looks like. We get base definitions from teams, and then we are able to automatically generate with one command the server-side resources, the client-side resources of the libraries, and the integration tests for all these things. So we can be very confident that when we're deploying these things out, they work because they're automatically verified. And we also have this extra tidbit of getting actual availability tests, which we may or may not have had before for certain resources. Because if humans are creating these things, it's possible somebody misses something. And the other thing we get here that is nice is the majority of like errors you'll find in once you're creating these resources is a mismatch in contracts. So I expected, as a human, I expected this to work this way, but it didn't actually work that way because there was maybe some like weird wording in some sort of spec. But because the spec is like one standardized definition file, that no longer happens because all the server side and the client side and the tests and libraries are all working off of a shared set of definitions. So everything, if there is a mismatch, it's not with the API team's work necessarily. It's a bug in some other part of the ecosystem that we can now track down. We don't have to worry about trying to debug our own thing. So here's like a case study for how the API definitions, the Yoyodyne definitions actually help with designing the API and the process. So for the wireless rate plans that you'll find in the wireless API, before the intention was to put them as a sub-resource on the device. And Yoyodyne didn't like that when we tried to generate things. It was like, you're not going to do that because the rate plans don't have a device SID on them, and Yoyodyne expects there to be a device SID there so that it can actually kind of plug it in there to the path and say, yeah, this is a rate plan of this device. So at first we were like, well, we've got to fix Yoyodyne, we've got to change this code. But then we realized, well, we're pretty confident this works for all the other APIs, so maybe there's something wrong we're doing here. And Yoyodyne actually caught something that we didn't really see because rate plans don't really belong to devices because they don't have a device SID. So devices do have a rate plan SID though. So really, rate plans are used by devices, but they don't really belong to devices because you can use multiple devices on a rate plan. So this actually helped us improve and say, well, if we do just you make it a top-level resource with the rate plan, then that works. So maybe that's the best way to design this, and it ended up being that that's kind of how it works, and that was the best way to do that. So the constrictiveness of Yoyodyne's definitions actually helped us design a better API. The other thing that Yoyodyne helps with is speed. That's the primary intention. And originally, if we wanted to add a brand new API to Starship, our API proxy, with library support, it could take anywhere from 1 to 4 weeks. This is because, especially if you have teams in different time zones, you have to do kind of user testing, see that, oh, well, there's one thing that doesn't work there because there was a mismatch in our contracts. Okay, we have to go back to the team and say, can we fix this? It might take like a day or two for them to respond because of different time zone or because they're working on a bunch of other things, they're trying to release this product. They come back to us, great. We were working on something else, we had to change course, et cetera, and it could take a while. With CPRs and with Yoyodyne, with libraries, we were able to generate the wireless API and 3 other APIs that we had that we wanted to switch over in less than a day. We were able to do that, and it was actually a couple of hours in that day. And that was mostly because it was the first time we were fixing bugs in CPR as we were finding them. And then so if we look at the responsibilities of the API team, well, we manage the public API layer, but now kind of Yoyodyne handles that. It does all the development there. We don't really do much for each resource. And the public REST, we manage the helper libraries, but Yoyodyne also does that. So I guess we don't have a job anymore, and we're just gonna chill out and, I don't know, here's my resume, I guess, if you wanna, if anybody has something. No. So instead, we decided to actually eliminate this last square. So a very interesting thing happened where we actually increased our bandwidth, and we moved further inside the company to take what we learned from developing the outside the public API and develop something internally. So we still work on the framework of Starship of our API proxy because we need to improve those things and make it faster and make it more efficient. We still work on the framework of the helper libraries of Yoyodyne. We still need to improve that and make it better and make it even more autonomous. But now we also work on an internal platform API, which I'm sure you'll be hearing about probably next year at Signal, where we're actually developing a Twilio for Twilio inside Twilio. And we also were able to adopt projects that were kind of considered side projects before, like Janitor, our AWS garbage collector, which was originally handled essentially by one API engineer, and now it's able to be a mainline product that the API team officially adopts. And a bunch of other useful tools that have been developed over the years. We've been able to make them official API products. So this is how basically the API team drove itself to obsolescence. Yeah, I hope you enjoy the talk. If you want to know more about Yoyodyne, there's no questions on the stage, but I'll be in the back there. And if also, for people that want to check out the new helper libraries, there are all of them except C#, which will be this week, are in release candidate stage. And there is a survey that is at that bit.ly link. And there's actually like a AWS, the $100 AWS card, I believe that's in the raffle if you do that survey. So if you want to try that out. And also that's where the talk slides will be. Thank you very much.